PhD student in Cornell IC3.
Hi, I'm Soumya, and I'm here to talk to you about bloXroute, a network for tomorrow's blockchain. So first, let's talk about the elephant in the room. The blockchains have been touted to decentralize many things. So as some examples, credit cards, global micropayments, the social media. So to handle the credit card transaction load, blockchains need to process about 5,000 transactions per second. To do global micropayments, you need about 70,000. Social media, you need about 200,000. Blockchains today do about 10. So there's clearly a gap. So let's talk about possible ways to solve this. So one naive solution here is to just try and increase the capacity. So for example, what happens if you try just increasing the block size in Bitcoin and seeing how far it can take you? And this works up to a point. So if we look at Bitcoin, at this time this was before SegWit, so Bitcoin had a less than 1% orphan rate at about 3 transactions per second. Ethereum during the same time period had about a 6% orphan rate at about 13 transactions per second. So we really need to look at why this is happening and why we can't just increase capacity. And this really boils down to how information propagates in the peer-to-peer network. Okay. So how this works is when a miner mines a block, they first start sending it to their neighbors. Their neighbors will then go and validate the block, and at that point, they'll start propagating it on to their neighbors. So this process will keep going very slowly, and eventually, you're hoping that the entire peer-to-peer network will get the block in time. So if we look at the key problem with the peer-to-peer network, it's heterogeneity. So suppose you have Alice who wants to send a block, and let's look at the path of that block from Alice to Bob. So what Alice will do, and here we're looking at only the shortest path, because it's the shortest path that determines the block propagation characteristics between Alice and Bob. So suppose Alice was able to send the block very quickly to its neighbors, who happens to be the super beefy Amazon EC2 instance with a lot of bandwidth and a lot of CPU thrown at it. So it can download the block very quickly, it can validate the block very quickly, and pass it on. The next hop happens to be a slow computer. So it's someone running maybe a not so beefy instance. And so they download the block much more slowly. They validate much more slowly. So when Bob gets the block at the end, there's actually not much throughput in this entire channel, because your throughput is limited by this node here, and your latency, while if you look at just the beefy nodes, if you keep pumping them up, you will get improvements in latency. There's diminishing returns, because it's going to be this slow node that dominates eventually. So the thing is, we know how to build high throughput systems. They exist. Netflix can stream gigabytes of data with no problem. And what's really their solution? Their solution is to trust a central authority. But that doesn't really work for blockchains, because the whole point of blockchains is we don't want to trust a central authority. We want to be able to decentralize control to many, many entities. So let's take a step back and think about what exactly do we want from our network layer. And what we want is the best of both worlds. We want the security of a peer-to-peer network. And by that, what we really mean is a completely oblivious network where it's hard to censor information based on where it comes from and what its content is. But we also want the scalability of a centralized network. So we want to support thousands of transactions per second, And we want blocks and transactions to propagate at low latency. We're talking about hundreds of milliseconds across the world. So what bloXroute does is it lets each network perform at its own strength. So if we look at just the peer-to-peer network, bloXroute keeps it around, but only for the security properties. And on top of the peer-to-peer network, bloXroute has a bunch of servers that are much beefier and a network on top of it that is optimized for high throughput and low latency. So what happens is the peer-to-peer network will audit this network and will make sure that it's actually behaving correctly. So that way the peer-to-peer network is not doing that much work, and most of the work is offloaded to this to the bloXroute network. So then we can sort of get this really nice sweet spot between having the performance of a centralized solution, whereas the control is still in the peer-to-peer network. So let's talk a little bit more about how exactly we do this. So fundamentally, in terms of performance, a bloXroute does one thing. It broadcasts data very, very, very quickly. And the goal here is to provide the abstraction to an end node of being directly connected to every other peer in the peer-to-peer network. And under the hood, unbeknownst to the blockchain peer-to-peer network, the peer-to-peer network is being used to check for content and being used to check that there's no censorship based on content or the origin. And a key idea here is that the exact peer-to-peer network structure is not revealed to anyone. So the first thing that we have to do is some of these links are only known to the two parties involved in that link. But first, let's talk about the performance. How do we provide the abstraction that you're directly connected to every other peer? And the trick here is cut-through routing. So cut-through routing, to see how it works, consider two nodes who are connected by a bloXroute gateway. So this is a timing diagram in networking, so time will go down. And we're looking at a block that's being sent. So this is essentially how the transmission looks. So the idea is at some point, the source node will start transmitting block at node 1. The first byte of the block will be transmitted to the gateway. And that delay here is the latency between these two nodes. The bloXroute server, before receiving the full block, it'll immediately start transmitting the first byte before it's done receiving the whole block. So that means that the destination will get the block much more quickly. Now, if you zoom out on this diagram just a little bit, the difference between having the bloXroute server in between the two nodes and not is this very, very small switching latency. So essentially what each bloXroute server does is it acts like a router in between the source and the destination nodes. So you get the abstraction here of being directly connected to all of the nodes. Now, let's talk about how we provide the security. So first, we provide obliviousness of content. And the way we do that is by sending in encrypted blocks through the network. So first, before you send a block, you encrypt it before you send it using some symmetric key encryptions. And then you listen to your neighbors. And remember, not all of the neighbors are public. So actually, it's very hard for the bloXroute network to sort of do an Eclipse attack and only send it to your neighbors, because bloXroute doesn't really know who your neighbors are. Now, the thing is, once you receive enough confirmations, you can then broadcast the key. Now, if bloXroute decides after unencrypting your block, it doesn't like the content of that block, sure, it can censor the key, but the idea is the key is very, very small. So it's very fast to propagate it through the peer-to-peer network if you need to. So what's happening is you're offloading most of the work of transmitting the block, the heavy-duty stuff, to the bloXroute network. And the peer-to-peer network is at the worst case, transmitting a small key. So to check the source, to make sure that the bloXroute network is not discriminating based on the source IP, what happens is you relay the blocks indirectly through one of your peers. And what this does is it obfuscates the origin, and it makes it very hard for bloXroute to tell who exactly is the original person that sent this block. And again, remember that you don't know who the peer's neighbors are, so it's even very difficult to get even a candidate set of these are the possible sources for this block because of the hidden peer-to-peer network structure. So one problem with the above two approaches is that you need blocks, and blocks are expensive, right? So the previous mechanisms are enough to provide neutrality. However, any misbehavior by bloXroute, if bloXroute decides to censor some block, is very, very costly. So you can lose block rewards, there's a higher probability of forks, and a lot of bad things can start happening. So to make misbehaviors low cost, we can send test blocks of dummy data. And the purpose of these test blocks is just to make sure that bloXroute is behaving correctly. So if bloXroute decides to engage in some kind of misbehavior, it'll happen on a test. It's more likely to happen on a test block than a real block. And these blocks are removed by the gateways, so the blockchain node actually doesn't know, it doesn't see this. It's happening sort of behind the scenes. So the security checks that we outlined above restrict bloXroute to two behaviors. It can either serve the network in a neutral manner, or it can just stop serving the entire network. And to prevent the second scenario from causing lots of damage is we have a lot of bad backup networks. And the idea behind these backup networks is if bloXroute stops serving a particular network, these networks can take over a bloXroute's functionality. And the way we do that is by open sourcing the bloXroute server so that anyone can run the server side of the bloXroute network. And the way we envision this happening is this is really a temporary fix until someone comes up with a long-term solution to fully replace the bloXroute network. So I'd just like to make a couple quick comments on how this is deployed. So each peer-to-peer node will run an additional process, a bloXroute gateway. The gateway provides two abstractions simultaneously. The first one is to the actual blockchain node. So if you think about like in Bitcoin, so you have the Bitcoin node and you have the bloXroute gateway running on the same machine. The gateway is talking to the Bitcoin node using the Bitcoin wire protocol. It looks like just a regular peer. And the gateway is also connecting to the bloXroute service and talking to and speaking the bloXroute protocol. And it's also performing all of the security checks and everything that I just covered. So this is incrementally deployable, so any gateways that connect to us will get the increased performance and we'll have these security checks being done. So ideally, it's going to incentivize people to actually go on our network. And I think the coolest part about this is the gateways are agnostic to the implementation of the servers. I didn't make any assumptions here about how exactly the servers are going to provide high performance. Sure, we do cut through routing, but the security checks don't depend on that. So what's nice here is that the server-side performance can be optimized fairly independently of the gateways and the security guarantees that they need to provide. So I've been talking mainly about Bitcoin and Nakamoto consensus. And here, bloXroute provides very strong security guarantees on the network itself. And the reason it needs to do that is that Nakamoto consensus makes very strong network assumptions for safety. If, for example, in the Bitcoin network, if you partitioned it so that the two halves of the network could talk to each other very, very quickly, but any blocks traveling between them take forever, eventually these two networks would fork, depending on what forever means. So it actually requires the network to behave pretty well for safety, so we need all of these heavy-duty tools. Now, the thing is, this strong safety guarantee is not true for every consensus protocol. For example, one of the most popular permissioned consensus protocols, PBFT, makes no assumption on the network for safety. It assumes a fully asynchronous network. So the nice thing about bloXroute is that some of the security techniques that we have, while necessary for consensus protocols that have strong network requirements, may actually be removable for other consensus protocols. And this really is sort of dependent on exactly how the protocol is structured and what it looks like. So, in conclusion, bloXroute is a rethink of the network layer from first principles. We provide very strong neutrality guarantees, and the reason for that is that we want to make it applicable to all consensus protocols. And there's a lot more to look forward to. So we're actively benchmarking it and deploying it on some of the most popular blockchains, Bitcoin Cash, Bitcoin, and Ethereum. And yeah. And I'm happy to take any questions. And here are the links to all our social media.
Do you want to come to the front? If you have questions, please move to the front.
Hello. So I wanted to ask if the servers are incentivized in any way to act as servers, or are they going altruistically?
Yeah, so there's a whole token model behind this to correctly incentivize bloXroute to keep providing the service. And I think that goes to our business model part. I didn't really want to delve into that for this talk, and I think the security part to me is the coolest part. So, but yes, there is a token model in order to make this work and make sure bloXroute is incentivized and everything. Yeah, I'm happy to talk to you about it after the talk.
Hi, my name is Gleb.
Hi.
Imagine, so you motivated this through scalability. Imagine that we increase the block size and start relying on bloXroute, and then hijacking attack, for example, happens where ISP start to censor traffic going to bloXroute nodes. And what we're gonna do then?
So if ISPs start to censor bloXroute nodes,
or make the traffic go into bloXroute nodes slower.
I mean, this is the same as with any other peer-to-peer network, right? You could look at, ISPs could start identifying what looks like Bitcoin traffic or Ethereum traffic.
Except
try and make
there are
that
much
slower.
more nodes in the Bitcoin network than there will be bloXroute nodes, right? Because they're expensive, because they have to serve.
So each node, I mean, there are defenses against these mechanisms, right? So you can look at things like honey encryption, or we can move IP addresses. So there's different techniques that would help with this. Again, we don't like, this is a bridge that we can cross when we get there, but it's yeah, the idea is that if the ISPs do decide to censor bloXroute traffic, there are mechanisms that that can be deployed to mitigate that. And also, if the ISPs do that, the gateways will also be able to detect this. So it's not that these checks are sort of agnostic to the implementation. So this will be sort of on the server side to mitigate these effects. That makes sense.
I have another really fast question.
Yeah, yeah.
So you said that bloXroute cannot blacklist specific miners, but can it whitelist miners that it likes and make it faster for those specific miners and less fast for any other miners?
So this will be checked using the approvable neutrality mechanism, right? So suppose bloXroute, so I guess there are two cases, right? So first is if bloXroute, suppose bloXroute whitelists some miners and blocks everyone else from joining the network, right? That's basically equivalent to what's happening today, where miners have their own private network, and it's just now bloXroute doing it instead of them. But if you're talking about the second case, where we sort of differentially sort of give two-tiered performance, there are ways to detect this. So I think our censorship mechanisms and using indirect relaying should be able to mitigate a lot of that.
Those details are in the paper, I guess.
Yeah, yeah.
Thank you.
Hi, one simple question on the network itself. So you're using cut-through routing. You don't talk at all about the congestion on the output links. So I presume either you're doing buffering and you don't see it at all, or what do you actually see in the operating network? How often do you see jitter from having to do store and forward routing due to congestion?
So yeah, so we're bottlenecked essentially by the input and output links. So the bottleneck for transmitting a block into the network is going to be the input link, the source, and most likely near the last mile there. And on the other hand, it'll be and for the downloading part.
I'm familiar because I'm a networking engineer person. So. So what do you do, and is the reason you don't talk about it in your talk because you just don't see congestion, or is there congestion and you have a lot of jitter on the...
We do see congestion, and we just buffer it until the source or destination can download it.
Okay, you might want to be clearer then, because you said just all cut-through routing, and that implies somehow you've solved congestion problems when you say that.
So by cut-through routing, this is not at the packet layer, so this is at the application layer. So if you're looking at a standard peer-to-peer network, they'll wait for the full block message because then they need to validate it. So this is an application layer cut-through routing. Thank you for that clarification. Yeah.
Then the other question is, you talk about having auditing as a backup, and so assuming that the auditing in some cases will actually find bloXroute made some kind of a mistake, what does the mechanism look like, and what's the latency that you would expect to see, for instance, like in BTC or ETH, for how long it would take for the peer-to-peer network to go and do a reorganization against what blockroute's propagated?
So the idea, and I don't think this was, the details for this are in the paper, but the idea is that each gateway will pick sort of an upstream node that's giving it blocks quickly and transmitting blocks out quickly. Now, if that happens to be a bloXroute server, and obviously the way we're running our network, it's most likely going to be a bloXroute server, then that's fine. And if it happens to not be a bloXroute server because a bloXroute is doing something weird, then we switch out to a different gateway. Then the peer-to-peer network essentially will kind of self-reorganize to picking sort of a good upstream node. So it'll so if it fails, it kind of depends on how much of the network it fails for. So suppose bloXroute fails for half the network. Well, then half the network will stop connecting to the bloXroute server's upstream peers, and it'll instead connect to a neighbor.
Okay. I think just as a comment, as a person seeing it, it would be useful, since you mentioned the auditing is a big part of the security guarantee, to give a little more details on how that mechanism would work.
Okay.
Okay, let's thank Soumya again.